and welcome you all to this lecture session of Applied Thermodynamics. So let us start where we left off. So we are discussing about quasi-static process and thermodynamic equilibrium. We have understood that these two are the basic requirements for a thermodynamic process. For any kind of thermodynamic process, we always assume that the process should be in thermodynamic equilibrium and all the intermediate states should maintain a quasi-equilibrium criterion. So this has to be followed. So let us start with that. So in the previous class we had discussed about this quasi equilibrium process. Today we shall be discussing much more deeper into it. So let us see what happens if we plot this whole concept into a graphical. So let us see the graphical aspect of this quasi-static process. So as you know, as I have explained earlier, so you can see that there is a certain weight W over here, and this W weight is divided into numerous number of weights. Okay, so this is quite understandable that these individual weights are much more lesser. So if we start removing these lesser weights one by one, then what will happen? The piston will start moving in the upwards direction. So let us assume at the initial state or at the equilibrium position, the pressure of the gas here and the volume of the gas were maintained at P1 and V1. So these are the initial states of the gas. Okay, now let us remove a single weight. So let us remove this weight. If we remove this weight, then obviously because of the pressure of the gas, the piston will move in the upward direction. So that means there is an expansion going on. That means the volume should increase and the pressure should decrease. So let us write this P1. So we have to remember that these changes are very small. That is, infinite small changes are going on. So pressure decreases by a small amount, by infinite small amount dP, and the volume increases by an infinite small amount, that is dV. So similarly we can see that there will be much more states which we can find. So let us plot these states in the thermodynamic diagram, in the PV diagram. Okay, so let us plot this one. So this one refers to the state number 1, which gives us the data of pressure P1 and volume V1. And similarly let us plot the second one, which refers to the pressure P1 minus dP and the volume V1 minus dV. So as you can see, the pressure has been reduced here and the volume has been increased here. So similarly, if we go on removing these weights, we can plot a thermodynamic curve. And if we join these points, individual points, then we shall generate a thermodynamic curve. So let us assume this is the initial state and the final state becomes, the pressure becomes P2 and the volume becomes V2. That means an expansion is going on, the pressure has reduced to P2 and the volume has increased to V2. So by the help of these quasi-static processes, by the help of these quasi-equilibrium states, we have plotted a continuous graph. So this is the important thing. So you have to remember all the graphs in thermodynamic diagrams are referred as continuous lines. This can be only achieved if the processes are quasi-equilibrium process. So until and unless the processes are not quasi-equilibrium, you can't draw a continuous curve. So this is the basic thing you need to understand. So wherever you will find that it is a dotted line drawn in a thermodynamic diagram. It represents a non-equilibrium process which doesn't maintain the quasi-static equilibrium. In the upcoming lectures, you will start to understand this also. This processes does have a connection with reversible and irreversible processes, but we'll not get that much deeper into these things. So the basic understanding which I need to tell you is that any thermodynamic curve which is continuous in nature, it suggests that it is following the thermodynamic equilibrium constraints, and it is also maintaining a quasi-equilibrium path. So this is the thing I want to mention here. So similarly, we can generate different curves. So these curves will be helping us to understand the next portions. The next portion, by that next portion, I want to mean how does energy transfer take place in thermodynamics? What are the mechanisms by which energy transfer takes place? So before understanding that, we need to know what is path function and what are point functions. So let us get into that. Okay. So just give me some time. Here it is. So here you can see three different lines. So this is an initial state and this is the final state, or this can be otherwise also. So let us assume that the final state is 2 and the initial state is 1. So from the thermodynamic coordinates you can easily understand this state refers to pressure P1 and volume V1. Similarly, this state refers to pressure P2 and volume V2. Okay. Now, what do we need to understand here? From state 1 and from state 2, if we don't know the quasi-static paths, we can trace any three paths here. We can obviously trace many other paths also, because we can join two different points with infinite number of lines. So we can generate infinite number of curves, infinite number of thermodynamic curves. So let us not get into that. We'll be discussing about what do we mean by path functions and what do we mean by point functions. So let us consider the thermodynamic state 1 has been changed to thermodynamic state 2 by following a path C. Okay. Similarly, let us assume a thermodynamic process has happened where the states have changed following this path and this one also. So there are three different paths A, B and C. Now from your common sense, you can easily understand each of the three curves have different amount of area. So the area in the thermodynamic curves is very important. Like, so since we do not have any kind of understanding about work transfer, let us give you an information. The area under PV curve denotes work transfer. How does it denote? Let us not get into that. Just remember this information. So this will help to understand what is the nature of these path functions and what are the natures of point functions. Okay, so area under this curve C obviously is less than area under this curve V and the area under this curve A. So we can let us write down here area of C is less than area B and area A. So depending on the paths, you can understand the values of the properties are the values of these specific functions, not properties, specific. So what I was talking about, you can easily understand depending on the paths, the values of this function does differ. So this is what we call as path functions. The functions which depend on the path in which the thermodynamic states has been changed. So the functions which are depending on the nature of the paths, on the thermodynamic paths, they are called as path function. On the other hand, you will find there are some properties like temperature, like entropy, like enthalpy, like internal energy. So these are the common notations. Let us not get into that because you don't know yet what do you mean by internal energy, enthalpy, and entropy. You do know. Similarly, you can take pressure and volume also. So this pressure, volume, temperature, they are dependent on this state only. They doesn't depend on the path. Okay, so this you have to remember. So there are some functions which depend on the path, and there are some properties which depend on the state only. So you have to focus on that. So the properties which are undergoing a cyclic process, like suppose if we consider a process like this. So for from state 1 to 2 and 2 to 1, so 1 to 1 does constitute a thermodynamic cycle. So you can easily say that the thermodynamic properties, the state values will have a cyclic integral of 0. Okay, so the values of the cyclic integral for the thermodynamic properties will be 0. So there will be no change when a cyclic process is going on. Whereas it doesn't have any kind of connection with the functions which depend on the path. Okay, so it can be a cyclic process, but it will be never, it can be 0 or it cannot be 0. It doesn't depend on the states. Okay, I hope I have make it clear to you. Okay, so why we are discussing about these path functions and point functions? Because work and heat transfer are path functions. We'll later describe that why they are called as path functions and not as point functions. And we'll be discussing now the process of energy. How do we define energy transfer or energy in case of thermodynamics? So it is quite different from the point of view of physics. So there is a sharp differentiation between the analysis of energy in case of thermodynamics. So let us get into that. So in case of thermodynamics, energy can be transmitted in two different ways. One is the mode of point functions, and the second one is the path functions. Okay, so when energy is being transferred as a point function, it means that it is referring to the energy in storage. Okay, it refers to specifically intermolecular energy, or we can sometimes we also call it as internal energy in a broader aspect. But intermolecular energy is the uh, much more specific one. Okay, intermolecular energy. So what are the examples of point functions, energy transferring as a point function? Like, let us consider a a gas is stored in a cylinder at a very high temperature. So we can easily understand that this gas has a very high amount of energy stored within it. What kind of energy it is? It is obviously because of the temperature it has within itself. Okay, so this is called as the intermolecular energy. So energy which is stored within the system by itself in virtue of the temperature or any kind of molecular energy. It can be the molecular kinetic energy, it can be the molecular vibrational energy. So the total summation of molecular level energies are termed as internal energy, whereas the energy which is only because of the randomness of the molecule which generates temperature are called as intermolecular energy. So there is a sharp differentiation between intermolecular energy and internal energy. Internal energy is the whole summation of all energies which a molecule possesses, whereas intermolecular energy refers to the energy which is only because of the temperature. Okay, the molecular motion which generates because of temperature, that generates an energy. So this is referred as intermolecular energy. And on the other hand, we will see there are some kind of energy transfer taking place by virtue of path, by virtue of the boundary transfer. That means there are some kinds of energy which can cross the boundaries. Okay, so let us consider a closed system. Let us consider a closed system here. It means that this is a closed system. Closed system. So this system has a kind of internal energy already within itself. So this is the point function, and there will be some kind of energies which will cross the boundary. So that type of energies are work, work transfer and heat transfer. So in general, you'll see that work transfer means that all the other energies collaborated with it. That means if we consider electrical energies are motivated to generate some kind of work, then it will be termed as electrical work transfer. If it is because of the fluid flow, then we will term it as uh, flow work. If it is because of the shaft, then it is shaft work. So there are numerous kinds of work transfer, but broadly, when the energy crosses the boundary, when the energy transfer place takes place by the through the boundaries, then we'll see there are two basic examples, two basic categories, that is work transfer, and the other one is the heat transfer. I hope you have understood it. So this is for internal energy or intermolecular energy, whereas the energy which takes place through the boundaries, where we are talking about the energy transfer which takes place through the boundaries, that we call as energy in transit. So this type of energies can be broadly classified into two categories, that is the work transfer and the other one is the heat transfer. And this work transfer can be categorized in numerous numbers, like mechanical work transfer, like electrical work transfer, like magnetic work. There are numerous kinds of work transfer available, but broadly they are categorized into work and heat. Okay, I hope so. So these two distinct natures of energies in thermodynamics, that is my point. I hope you are getting it. So energy in storage and energy in transit. Energy in storage refers to the intermolecular energy, and energy in transit refers to the all kind of work and heat transfer possible. So now we'll be getting into the uh, what do we mean by work transfer actually. Okay, so here you can see and diagram, a system is given here. So let us just focus on this W's. Okay, do not focus on this Q's. This Q refers to the heat transfer, whereas this W's refers to the work transfer. So let us just not focus on. Okay, so in mechanics, we know that the work is done by a force as it acts upon a body moving in the direction of the force. The magnitude of the force multiplied by the distance it which the body has traveled gives us the magnitude of work. Okay, so it is a scalar quantity. If we know that things, this is full level things, you know that. But in case of thermodynamics, you have to understand this work in a different way. So there are two basic ways. In the first case, you have to understand, uh, obviously you know the concept of system and surroundings. So system is the point where all our attention is focused on, whereas surroundings is that part of the whole environment through which the system is interacting. That means the part of the universe with which the system is interacting is called as the surroundings. Okay, now there will be some cases where you will find the motive force. That means the force which is uh, doing this work can come from both the system as well as surroundings. Sometimes you will find the work is done by the system, and sometimes you will find the work is done by the surroundings. Now there is a general convention, there is a general sign convention that if work is done by the system, then it is treated as positive work. But if the work is done on the system by the surroundings, then it will be treated as negative work. Okay, so work work done by the system on the surroundings, work done work done by mm, work done by. So as you can see here, I have written it here. If the work is done by the system on the surroundings, it will be treated as positive work. But if the opposite happens, if work is done by the surroundings on the system, then it will be treated as negative work. Like it is already given in the diagram here, positive plus W work and minus W work. So let us solve a simple problem here. So here you can see there are three types of work which is going through the boundary. So this is the boundary for you. This is the boundary, and you can see three types of work: one, two, and three. Three types of work are crossing the boundary. Now, can you please tell what will be the total summation of work? So you can uh, I can give you some time for it, or it is very simple. So as per the convention, if the work is done on the surrounding, then it is positive. So you can see this W2 work and this W3 work is being uh, done by the system on the surroundings, whereas this W1 work is done by the surroundings on the system. So the net work done will be W2 plus W3 minus W1. So it is quite simple. Okay, so the convention of heat obviously differs from it. We'll be discussing it later, but for your information, may say you here, if the heat transfer is taking place into the system, that means heat transfer is taking place from the surroundings to the system, then it will be positive heat transfer. Whereas if the heat transfer is going out of the system to the surroundings, it will be treated as negative. So here it will be Q1 because it is coming from the surroundings to the system, and it will be Q1 minus Q2. So as I have told, there are two types of energy transfer possible in thermodynamics, one of which is the energy in transit, and the energies which are crossing the thermodynamic boundaries are work transfer and heat transfer. So both the examples are given here. So let us move on to the special types of work, the most important of them, which is PDV work or displacement work. So we will be now discussing about this PDV or displacement work. So as you can see a diagram over here, a certain mass of gas is under the effect of a piston which is exerting a certain amount of force F on the gas. So this is an equilibrium position. That means the pressure exerted by the gas is exactly same the pressure exerted by the piston on the gas. So from the point of view of mechanical equilibrium, we can say this P is equal to F. This P is being exerted by gas on the piston, whereas this F is being exerted by the piston on the gas. Okay, you can take it otherwise also. So P is equal to F, which refers to the the mechanical equilibrium uh, condition. Now what happens if this this if the pressure exerted by the gas is little bit increased? Okay, so the gas is, we are applying some kind of pressure so that the piston can move in the upwards direction. That means the gas is getting expanded here. So the expansion of the gas is taking place, as well as the piston is moving in the upwards direction. So let us take an certain amount of expansion has taken place. Let us consider this is the initial phase or initial state here and the final state. So let us draw a diagram for your better understanding. So okay, I am sorry, because there is no need to draw the diagram here. If you see this diagram very much minutely, you will find this refers to the initial position of the piston, and after the expansion has been taken place, there is an elevated position of this piston is referred here, and ds is the amount of displacement of the piston, or in other words we can also say initially this was the boundary of the closed system between the piston and the cylinder, and this boundary has been moved in a upwards direction by a certain value of ds. So this is all happening because of the motive force of pressure which is applied by the gas on the piston. Now we are treating this gas as our thermodynamic system and the piston as our surroundings. So we can easily understand from our previous ventures, from our previous discussions, we can easily understand that if the work is done by the system on the surroundings, then we treat this kind of work as positive work. So we are treating the gas as our system, and the gas is exerting some amount of force on the piston, by virtue of which a certain amount of work is being done. So uh, now we need to calculate the amount of work. Now why it is called displacement work? As I was referring you, this was the initial position. The piston and the gas, they both together constituted a closed system. Now, after the expansion has taken place, the boundary of this closed system has been displaced from here to here. So there is a displacement of the closed system boundary taking place. Okay, this is the basic point you need to understand. So when you will find, so there is some kind of displacement of the boundary of the closed system is taking place, then you can term it as displacement work. In other words, it is also called as PDV work. So now I will explain why it is called as PDV work. So let us assume the area of this piston is A. Okay, the force exerted by the gas is P. So A is the area of the piston, P is the force applied by this gas. So now from the definition of work we know, or I'm sorry, this P refers to the pressure exerted by the gas. So pressure into area, you know, this refers to the force. Okay, so pressure into area is the force, and the you have to you need to know that amount of displacement. The amount of displacement is already given to you. It is by ds. Now A into ds refers to dv. So this pdv comes from here. So this this interpretation of pdv is for an intermediate state only. Okay, so like the initial state was p1 v1, and the final state becomes p2 v2, and in between these two thermodynamic state we have taken a certain state where the pressure was P and the amount of displacement of the closed system boundary was by ds amount. Okay, so for that case only the work done by the gas on the piston becomes pdv. Now when we need to calculate the total work done, so this PDV, once again I am saying, this PDV for the this PDV is only for the intermediate state. But if we need to know the total work done, then we have to integrate. Now what will be the limits? The limits will be the change of volume. That means the initial volume and the final volume. So when we see the limits are v1 to v2, that means the initial volume and the final volume, then we can calculate the total work done. And you have to remember, this p should be always a function of v. If it is not a function of v, then we can't calculate it. We can't calculate the exact data. So this p can always be expressed in the function of v, so that the work done becomes very easy. Okay, so this pdv work or displacement work is now explained to you. I hope you have understood. So this is, so displacement work means that it's displacement of the boundary of the closed system. The amount of displacement is what becomes important. So the pressure, area, and the amount of displacement. So that is why it is called as displacement work. And why it is pdv work, it is quite understandable to you. You can easily understand why it is called as pdv work. Now we shall be discussing about the different work transfer, or I'm sorry, now we'll be discussing about the displacement work for different thermodynamic processes. As I said in the previous lecture, we shall be discussing much more about the different thermodynamic processes like isobaric, isochoric, isentropic, and other all. So now the time has come and we shall be discussing much more about this thermodynamic processes, and we shall calculate the amount of displacement work done by these thermodynamic um, processes. Okay, so let us take the example of isobaric process. So As you can see, I have drawn the graphs for three different thermodynamic processes. So this is the isobaric process, which refers to the constant pressure process. This is isothermal process, which refers to the constant temperature process, a thermodynamic process where the temperature remains constant throughout the system, throughout the process. And this one is for isochoric. So this refers to the constant volume process. Okay, now our objective is to calculate the PDV work for all of these three processes. So let us start with isobaric. Then we'll go on to isochoric, and then we'll move on to isothermal. So because as isothermal will take a little bit of time, so we'll do in the later part. Okay, so now let us consider this process 1 to 2. So in the first case, the coordinates or the states was P1 V1. In the second case, it became P2 V2. Now as the pressure is constant, it is quite evident that we don't need to write P1 or P2, because we can only write P. That will be sufficient. So a constant pressure is maintained throughout. So if we need to calculate the PDV work, what was our formula? The formula was integration of P dV. What were the limits? The limits were V1 to V2. So V1 to V2 means initial volume to the final volume. So since P remains constant, we do not need to correlate with dV. So we can treat this P as constant, and we can integrate this dV between the limits of V1 and V2. So which gives us P V2 minus V1. So I am not getting into integration. This is quite very simple. So the work done in isobaric process is P into, sorry, this it is P into V2 minus V1. Okay, so you have to remember these formulas. Okay, so you have to um, give very much importance to this formula, because to solve different numerical problems, these formulas will be required very much. Okay, so let us um, erase this, because uh, it is quite evident that the pressure remains constant, volume is the only one parameter which goes on changing. The integration of dV yields the value of V2 minus V1. So the net work done becomes P V2 minus V1. So let us just clear this isobaric thing. Now we shall move on to the discussion of isochoric process. Now what happens in isochoric process? The pressure does change here. So let us take this as the volume remains constant. We have taken V as the coordinate. That indicates the volume is not going to change. Since the pressure changes, we have wrote down P1 and P2. So if we understand this formula PDV, then we can easily understand this dV for any isochoric process is 0, because there is no change in volume. The volume is not going to change, the volume remains constant. So this dV is 0. So that gives us the answer. The answer will be 0. So in case of isochoric process, no work is done. Okay, so I think you have understood it. So in case of isochoric process or constant volume process, the work done is 0. But what happens in case of isothermal process? Okay, so that is our discussion now. we shall be discussing about this thing now. So the work done is integration of P d V, right? So the integration is P dV. So V1 to V2. So I am taking the general coordinates P1 V1, P2 V2. I am not writing it now. So PV is equal to C. C for constant. Similarly, as we know, these two states are P1 V1 and P2 V2. P1 is the initial pressure, P2 is the final pressure. Similarly, V1 and V2 refers to the initial and final volumes of the state. So becomes equal to PV becomes equal to, let me just clearly write this, P1 V1, which is again equal to P2 V2. So do you get this? Since P1 is the initial state, V1 is the initial volume, the multiplication of these two, it is already referred here. PV is equal to constant. Similarly, P1 V1 will be constant, P2 V2 will be constant, and from this equation we can write P is equal to P1 V1 by V, as well as we can write it P2 V2 V2 by V. So let us just replace it here. Okay, so we will be just replacing the value of P which we had obtained here, and then we shall go on integrating it. So it will be P1 V1 into dV by V. Since P1 V1 are the constants, we don't need to correlate with this V, so this can be treated only as constant, and integration of dV by V yields ln V. ln V with the limits of V2 and V1 will give you ln V2 minus ln V1. Okay, so this will be the final answer. Final answer can be much more simplified. You know the logarithm properties. It can be also written down as, um, just removing it. This is very simple. The school level mathematics. You have already uh, you know about this logarithm things. So it will be ln v2 by v1. So the ultimate result, or the ultimate work done by the system in an isothermal process becomes P1 V1 into ln P2 by V1. This can be also sometime written as ln P1 by P2. So these are all similar results. You need to just change the values. Okay, I hope it is understandable to you. You have found all the informations you needed. Now you can easily calculate the displacement work for isobaric and isothermal process. So now we shall be moving on to the work done calculation for adiabatic process and polytropic process. So this will be a little bit tedious calculations, because it refers to much more variables. Okay, so it will include much more variables, so it will be little tedious. So let us discuss about that. So let us discuss about adiabatic process. So I have told you earlier, adiabatic process means that there is no heat transfer going on in an adiabatic process. Okay. So according to the thermodynamic diagram and according to the pressure volume relationships, it maintains a relationship of PV to the power gamma equal to constant. Now what is this gamma? This gamma refers to Cp by Cv. Okay, Cp means the specific heat at constant pressure, and Cv means the specific heat at constant volume. That means whenever the amount of heat which is required to increase the temperature of 1 kg fluid by 1 degree Celsius at a constant temperature is called as the specific heat at constant pressure. So this has a certain thermodynamic relationship with the internal energy and enthalpy. We shall not get into this presently at this moment. So just for your information, you just know this fact. uh, the amount of heat which is required to increase the temperature by 1 degree Celsius for 1 kg of fluid is called as the specific heat. So if this process is maintained in a constant volume, then it will be treated as specific heat at constant volume. And if the similar process is maintained in a constant pressure process, then it will be called as specific heat at constant pressure. Okay, so gamma is the ratio between this Cp and Cv. And here you can see for diatomic gases, like oxygen, nitrogen, it will be 1.4. For monoatomic gases, it will be different. It will be near about 1.2. And for triatomic gases, it will be also different. Okay, so now our primary concern is to calculate the PDV work in um, adiabatic process. Okay, so we know that uh, we'll follow the same rule which we are following for the last three processes. So it will be PDV, and the limits will be what? The initial volume and the final volume. Now here you need to understand that there is a relationship like this. So it is quite similar as it was for isothermal process, just the values change. Okay, so it will be P2 V2 gamma. Similarly, we can write this P this P as this P can be written as P1 V1 to the power gamma by V to the power gamma. That is very simple. Okay, so just you need to put this value here. So which, sorry, just give me a little bit of time. P1 V1 to the power gamma into dV by V to the power gamma. The limits will be V1 to V2. Okay, this is very simple. Okay, and you know this P1 and V1 to the power gamma, they are nothing but the constant. So they will so they doesn't have any part to play in this integration. So the final integration will be something like this. Okay, so it will be also gamma minus 1. So I know that you haven't forgotten the tricks of integrations. Okay, so the ultimately the result will be P1 V1 to the power gamma minus P2 V2 to the power gamma by, it will be gamma minus 1. So the calculations regarding this is your assignment you need to do by yourself, and you need to find out how does this this result come from this step. Okay, so this is your job to do. Now a similar process like adiabatic one is also sometimes given in your problems. It is called as polytropic process. So just clearing this part, I'm leaving this part for some time. So it will be termed as polytropic process. Now for adiabatic process, the pressure volume relationship was, so the pressure volume relationship was PV to the power gamma equal to constant. For polytropic process, it will be PV to the power n. Okay, so this gamma is called as, the gamma which is mentioned in the adiabatic process is called as adiabatic index, and this n is called as polytropic process. So you will find the the calculation of displacement work in any kind of polytropic process will follow the same formula like as it was in the adiabatic one. Only the index will change. So the index was gamma in case of adiabatic process, but in case of polytropic process it will be n. So I hope you will be able to calculate this, because it is uh, almost, it is actually same with that of the adiabatic process. So there is no difference, only gamma is replaced by n. Okay, so I think I am done with this part, because I have shown you the calculations for all of the general and the most common thermodynamic processes which are available here. Okay, so now we shall move on to a problem, a thermodynamic problem, where these formulas will be used very much. Okay, so let us see this problem here. So as you can see, a piston cylinder device operates 1 kg of fluid at 20 atmospheric pressure. The initial volume is 0.04 meter cube. So you can see, just I am just writing down the basic informations here. 1 kg, the pressure is 20 atm. I don't know it is the initial or final one, because probably it is the initial pressure. Okay, huh. Yes, it is the initial pressure. The initial volume is 0.04 meter cube. So V1 becomes 0.04 meter cube. Okay, so this is very simple. I'm just writing the data which are given in the problem. The fluid is allowed to expand reversibly following a process PV to the power 1.43 equal to constant. So this is a polytropic process, right? So PV to the power 1.43 equal to constant, right? So these are the informations which are available till now, so that the volume becomes double. So this is a very useful information. The volume, the final volume is given as the double of this. So we can write V2 as 2 into V1. The fluid is then cooled at constant pressure until the piston comes back to the original position. Keeping the piston unaltered, heat is added reversibly to restore it to the initial pressure. So for this problem, we need to, there is a serious need to draw the diagram. Until and unless if I don't show you the thermodynamic diagram, it will be very hard for you to understand the problem here. Okay, so this is the first process, which is following this PV to the power 1.43 equal to constant. Okay, then what happens? The volume, the volume which was initially at V1, it becomes, so let us just extend it here so that it can be shown that V1 V2 is equal to 2V1. And then what happens? The fluid is then cooled at constant pressure. So that means a constant pressure process is happening here until the piston comes back to the original position. Okay, so the original position means it has to be linear with this point. So this point and this point has to be must lie on the same line. Okay, and then for the last process, what happens? Heat is added reversibly to restore it to the initial pressure. So that means heat is added here. So can I am showing you the directions. Let us use another ink here. It will be better for you to understand. So this is the first process. 1 to 2. Okay, I have just missed my thermodynamic diagrams here. The axis I have missed, it is P and V. Okay, so the drawing is entirely based on PV diagram. Okay, so initially the initial state is referred by point 1, then the volume becomes double, so it refers to the state 2, and after that what happens? It is the fluid is cooled at constant pressure. So that means from this state 2 the fluid comes to the state 3, and then afterwards heat is added reversibly. Okay, so you will be not getting the fact reversibly, but you can understand that heat has been added. If heat is added, then what will happen? The volume will remain same, but the pressure will be increased because pressure is proportional to temperature. Okay, so this becomes 3 to 1. So this is the thermodynamic plot for U. Now we need to calculate the work done in the cycle. So this first process is what? It is an polytropic process. This is a polytropic process. I'm sorry. Uh, for process 2 to 3, it is an isobaric process, and for process 3 to 1, it is an isochoric process. Now you know, in case of isochoric process, no work is done. So the work done in isochoric process or process 3 to 1 is 0 for this problem here. So we need to calculate the work done for the process 1 to 2 and process 2 to 3. So these two tasks has been given to us, and then when we uh, when we have found out the work done by the first process, that is process 1 to 2, and the second one process 2 to 3, we need to sum it up so that we can calculate the total work done. Okay, now let us start with the first process. So you know, I have just discussed it. The work done in polytropic process follows this formula: P1 minus P2 V2 by N minus 1. So this is the work done for process 1 to 2. Now you know pressure is given as 20 atm. Now what you need to do? You need to convert this atm into bar. Okay, you need to convert this atm into bar or kilopascal, whatever you wish. Okay, so if you convert this, you will find the you can easily calculate it, and you know the volume at state 1, it is given as 0.04. Now you also know that P1 V1 to the power 1.43 is equal to P2 V2 to the power 1.43. Now I think there should be no question about this statement, because you know PV to the power 1.43 is constant. This is the nature of this process. So for state 1, P1 V1 to the power 1.43, and for state 2 it will be P2 into V2 to the power 1.43. So they will be same. They has to be same. They must be same. Okay, and you know that V2 is equal to to V1. So if you equate, so as you can see, the problem is almost solved here. So what we are discussing, P1 V1 to the power 1.43 is equal to P2 V2 to the power 1.43. So it will be something like this. So this ATM should be converted into bar following this relationship, and ultimately you will find this P2 is equal to 7.417 bar. Okay, so this calculation you need to do by yourself. But so now you have all the data. P1 is equal to 20 atm. If you convert it into bar, it will be something like this. So these calculations you need to do by yourself. So this will be 20.265 bar. Okay, so now you have P1 as 20.265, V1 as 0.04 meter cube, P2 as 7.417 bar, and V2 as 0.08, because it is the double of V1. So if you put these values and multiply this whole equation into 100, then you will find the work done in kilojoules. Ultimately the work done will be 47.82 kilojoules. So this calculation you need to do by yourself. So for the first process, the polytropic process, you find the work done becomes 47.82. So this problem was very simple. Now there is something left over. The work done for the process 2 to 3 needs to be calculated. So this is an what? This is an isobaric process. So what is the formula for isobaric process? We have just discussed it. It will be pressure. The pressure here maintained will be equal to the pressure at state 2, which we have already calculated. So work done for process 2 to 3 will be pressure at state 2, and what will be the differences in volume. So let us just write down this state, so it will help you to understand. So at state 3 the pressure remains same, so it is P2 written over here, and the volume changes from V2 to V3, which is again same with V1, because you know this is an isochoric process or a constant volume process, so the volume will be same. So V3 is equal to V1. So the work done will be calculated by the formula V2 minus V3, and this V3 is nothing but V1. So I will just replace this V3 by V1, and ultimately you will find the result to be, now see, it will come in negative. That means what happens here? The surroundings is doing work on the system. Okay, now if we consider the fluid as our system, we have considered the fluid as our system. That means the piston is doing some kind of work on this fluid, okay, which measures to be 29.65 minus 29.65. So let us just remove these things um, for our better understanding, because we are going to the end of this problem. As I told you earlier, you know this is an isochoric process. So for isochoric process, the work done is 0. So the total work done will be summation of W1 to 2 and W2 to 3. So this is the work done by these two different processes, and the total and the final result will be 18.17 kilojoule. Okay, I hope that uh, you have understood this problem, because this is very simple. You just need to understand the nature of the thermodynamic process, and you will find a certain thermodynamic relationship is always given to this certain process. A pressure volume relationship is given to you, and whenever you know that pressure volume relationship, you can put it into the PDV equation, and then you can get the desired data. If sometimes you will find the PDV relationship is changed, because this problem was from our sphere. That means we had discussed about these 5 different processes, and the problem mentioned here included those processes. Okay, but sometimes you will find there are different relationships. So that means there is a functional relationship between pressure and volume. If you know that relationship, you have to connect it with, you have to express the term P in terms of V. So you just need to express P in terms of V, then it put it on the PDV equation and integrate between the limits of initial and final volume. So any kind of problem where you know the pressure volume relationship, you can easily solve it. And one more thing, you need to understand, if it is mentioned, obviously you need to understand the work is done by the system or it is done by the surroundings. That you need to understand, and that hints will be available in the problem itself. So you need to read the problem very sharply, very minutely, so that it becomes easy. So this is for today's lecture. This is for this third lecture, and in the next class we shall be discussing about other types of work transfer, and then we shall move on to the concept of heat transfer. So I just want to recap um, what I have said for this whole 50 or 60 minutes. The thing is that, because I have discussed too many things and you need to remember this, I need to provide you a certain gist so that it helps you. So the basic point is that in case of thermodynamics, energy can be transferred in 2 different ways. Energy can be treated as point function, or it can be treated as path function. That means you can find energy in stored form, and you can find energy in transit form. That means energies which are crossing the boundary. Heat and work transfer are the examples of energy in transit. So this, whenever you will find heat and work interactions are taking place, that means it is a boundary phenomenon. That means energies are crossing the thermodynamic boundaries. Okay, and then we moved on to the concept of work. We moved on to the concept of path and point function. So there are some functions which depend on the path. So work is one of them. So work transfer is always one of them. So just to mention it, so this was the curve. Okay, so this was PV and this was V. So one thing you should remember for your lifetime: area under PV curve is the net work done. Okay, so if you consider this curve, C, B and A, you can easily understand, depending on these three depending on these 3 different paths, the net work done will change, because the area under these 3 different curves are obviously different. So it is quite evident that the area under C is much less than the area under B, and consequently the area under A. So the work done by the path C will be obviously less compared to B and A. So work done is always a path function. But there are certain properties which doesn't depend on the path. It only depends on the certain state. So they have certain values defined, already defined for this state, and they always uh, the measurement of these properties depend on the nature of the state. And for any cyclic process, there is no change for these properties. Okay, since they depend on the state, for any cyclic process there will be no change. So, and then what we did, we calculated the work. So we discussed about then what we did, we discussed about pdv work or displacement work. We understood what do we mean by displacement work, why this word displacement is very important. It refers to the displacement of the boundary of the closed system which we are referring to. If we consider a piston cylinder arrangement where both the gas contained in the cylinder and the piston together constitute a closed system, and when you find the boundary of the closed system is getting displaced, that means an expansion of the volume and the mm, pressure is getting reduced, so that it is generating some kind of work. This is a non-dissipative kind of work, and you have to remember, every time this work is done, the quasi-static equilibrium is always maintained here. Okay, so this is a non-dissipative kind of work, and for each process, for each state, the quasi-static equilibrium is maintained. So this is, all of this is hypothetical, but we have already told you that this thermodynamic equilibrium concept and the quasi-static process, these two are the primitive assumptions, and they are very important. Okay, they are very important. Okay, so what we are discussing, we are discussing about the displacement work. So whenever there is a certain amount of displacement of the boundary of the closed system, that induces some kind of work which we define as displacement work. And when we start to calculate it, we find this work to be defined as pdv work. So what you need to do to calculate this amount or magnitude of this pdv work, you just need to express this p in terms of v, so that you can perform an integration, and therefore you get your requisite or required value. We have also shown for different processes, for 5 different processes, how does the work transfer can be calculated. And if we have also solved a problem where you have I think you have got a certain understanding how to solve the problems. Okay, so I hope this was a good session for you. You have understood the basic concepts of work transfer. In the next class, we shall be discussing about different types of work transfer. Okay, we'll be discussing about electrical work. We'll be discussing about stirring work or paddle wheel work, and we'll be discussing about flow work. Okay, then we'll be moving on to the concept of heat transfer. So thank you, thank you all for being with me, and so this is the end. I end it here. Okay, goodbye.